Well, hello. My name is Andrei Novoselov, and I work at the Gcore company. And today I'm going to tell you about how we shoot our old Kubernetes orchestrator and move to the new one. So we'll talk about OpenStack Magnum and Heat, obviously. Then we'll take a look at the alternatives. And then we'll talk about cluster API, and we'll talk about live production migrations from one orchestrator to another. And then we'll learn what perfection is. So before we begin, let me quickly introduce myself. I work at the Gcore company. We are a public cloud provider. We have more than 20 locations around the globe with our public cloud services. And my team is responsible for Managed Kubernetes as a service, function as a service, container as a service, logging as a service, database as a service, and basically anything as a service is inside my responsibility zone, but the operations side. And today we are going to talk about Managed Kubernetes as a service. So when I was promoted to a team lead at Gcore, I was told that congratulations, now you're responsible for the Managed Kubernetes. And I was like, wow, that's so exciting, and how does it work? And I was told it's easy, it's just OpenStack Magnum and Heat, and you'll learn about it. So let's learn about it, just like I did. So there's two basic components in the OpenStack way of orchestrating Kubernetes cluster. First is Magnum, and what it does, it orchestrates containers, clusters of the containers, and it supports Docker Swarm and Kubernetes. The second component is Heat, and it creates cloud init configuration for all the Kubernetes nodes. It updates the applications inside those nodes and, well, reconfigures it. And it operates with Heat templates or Heat stacks. So the main components of Magnum are, like in any other OpenStack API component, it's Magnum API, RabbitMQ, and Magnum Conductor. So API receives some tasks, it puts it to the RabbitMQ, Conductor gets them and makes them done. Heat is pretty same. It has Heat API, RabbitMQ, and Heat Agent, and one more component, which is Heat Agent. And the most fragile components, the not so reliable, let's call it this way, are RabbitMQ and Heat Agent, and we'll get to it a little bit later. So what are the limitations of the Magnum and Heat out of the box? There's no control plane isolation at all. And, well, it's an OpenStack API. And we need to somehow, if we want to make it a managed service, to hide it behind our Gcore Cloud API. So this is our approach of adopting it. And this is architecture of the first version of our Managed Kubernetes solution. So it's all is inside the client's private network. And we have 3 virtual machines, which are control plane nodes and some worker nodes. And we separated the control plane from our users. Well, pretty easy. We have some firewall, which blocks all the traffic from the worker nodes, except the traffic through the free load balancer, one to the etcd, second one to the Kube API, and the third one for the Kube DNS. Everything on the control plane is run as a systemd unit and with the podman. On the worker node, only kubelet is run as a systemd unit inside the podman. Everything else is run by the container runtime, which is Docker in our state. And the operating system is Fedora CoreOS, and that's the limitation. So what are the pros and cons of this approach? Well, the biggest plus is that it's an OpenStack, so it has a big community. Community will write new features for us, and, well, we can save our time for doing something else. Cons, well, we have an extra RPS for our cloud API because it's proxying all the requests to the Magnum. It's fragile, like really fragile, and there's a problem with the observability. So the control plane is inside the client's private network, and, well, it's pretty tricky to get anything from the client private network. And when we started, there was no bare metal nodes out of the box, so only virtual machines. And the spin-up time for a Kubernetes cluster was 20 minutes average. So the biggest cons are fragile and observability. If anyone asks me what does it look like to operate Magnum in production, well, I'd say it's as easy as ride a bicycle, but it's on fire and everything around is on fire and we are in hell. So if anything happens to RabbitMQ, well, then probably your heat will not tolerate it, and heat stacks would fall into the error state, and there is no CLI way to make them work. So you'll need to deep dive into the production database and do some updates. And heat agent, well, to keep it short, it took about 4 hours to take the production cluster back to the normal state after some malfunction in the region in its Rabbit. And if you have 100 clusters, then that's 400 hours, and well, that's too much. And if you're fixing something, and well, heat agent just keeps updating, so there is no node recreation or node immutability. If you need to update something on the node, then heat agent just reconfigures systemd units and its configs and so on and so forth. So after every failure, well, at the start, we had like 2 black cats. And we had a malfunction, we had to fix it, and there was a small configuration drift, and both of the cats became black. White, my bad. And after another malfunction, one of those clusters goes down, and we fix it other way, and now we have 1 white cat and orange cat. Yep. And my point is, we had no immutability, and we had to fix something with our hands, and we had a huge configuration drift. And we knew all our core customers and their clusters, and we had to remember, well, that one was fixed first time and that day, and that day, and then a difference from the other. So it works for the small amount of clusters, but if we're talking about hundreds, well, it doesn't. So working with Magnum, it is more like working with pets versus working with cattle. So another one, con of Magnum. So the Kubernetes version support. For example, right now we are on the Z, and it's only 1.23. So, but even if you'll get to the latest Magnum version, it will support only Kubernetes 1.27. And this screenshot was done 2 days ago. And yesterday we had the release of 1.30. So it's a little bit outdated. But the point is, the current supported Kubernetes version are 1.28, 1.20 now, and 1.30. And, well, if you get the latest Magnum, you will not get the supported Kubernetes if you get it out of the box. So, well, to summarize, is it perfect? It's obviously not. Is it even good? Well, I would say no, it's not good. So how can we prove it? Well, we have to improve the stability, first of all. We have to add bare metal node support. We need to add faster the newest version of Kubernetes. And we have to improve observability because it's too annoying to get into the client's private network to know anything about the kube API. And we need to improve cluster spin-up time because 20 minutes is too much. And while we are doing all of this, we need to hire more ops people to manage all those things with resurrection of dead clusters, which I mentioned. So the question is, should we invest in evolution of Magnum? Or maybe we should think about the revolution and change our orchestrate. So before answering that question, let's just talk about the evolution itself. So why don't zebras evolve into ultramarines and killer lions? Because ultramarines are obviously more efficient versus lions than the zebras which we are having right now. And there's a problem in the evolution theory which is called the locum extremum or local maximum. So let's imagine that you are this zebra, and the only way to evolve is to get better, and then you have to go up and up. But your current zebra architecture have some limitations, and sooner or later you'll be the best zebra ever. And when you get to the local maximum, you will only get worse. But you can even see that the next hill, well, you may become a better ultramarine, but to do that, you'll have to go down your hill, your zebra hill, and that will make you weaker and you might disappear. So when you get to your local extremum, that's the most you can do if nothing changed around you. And so you got the idea. This is probably the best Magnum ever which would be created, and this is the Magnum number 15. And should we, well, maybe there is some technology which the perfection is somewhere there, but its imperfect form, which is current form, is much better than the best Magnum that we ever can have. So what if? Let's just take a look what we have on the market and compare all the available technologies. So first of all, I don't know, let's start with microcates from Ubuntu. Maybe let's add the OKD from Red Hat. Maybe Rancher by Suse, maybe Deckhouse by Flant, maybe Gardener by SAP, maybe Ansible playbooks would do the thing. Nope, it would be too much time to compare them. We will talk directly about the cluster API today. And so from my point of view, it looks like this. Here's the Magnum number 15, and here's the cluster API 1.7. It's probably much better than the Magnum could ever be, and did have the potential to grow up. So yeah, that's the best zebra, and that's what we can get from the cluster API. So what is cluster API? First of all, it's a SIG group inside the Kubernetes, so it's done by the Kubernetes team. It, just as Magnum, manages the cluster lifecycle declaratively. It works on-premise and in cloud. It defines the common operation like creation, update, deleting, and scaling of the clusters. It provides the default implementation. It provides the ability to swap out the default implementation for the alternative, and it can be extended to support any infrastructure. And actually, what's its architecture? It's really easy, just 4 binaries. Well, it's a copy controller manager. It's a bunch of controllers. Well, you need a Kubernetes to create another Kubernetes because copy is a bunch of controllers inside the Kubernetes. I forgot to mention that, my bad. So, controller manager is a single pod with a bunch of controllers which reconcile cluster API custom resources. We have also a Bootstrap controller manager and control plane controller manager. Those guys create cloud init configuration for our worker and control plane nodes. And there's an infrastructure provider which connects all these guys to the infrastructure you have and which can be swapped at any time. So what do we have out of the box? For the Bootstrap controller manager, we have different engines such as kubeadm, Microcade, Talos, EKS from AWS, and that's it. For the control plane controller manager, we have the same kubeadm, Microcade, Talos, and Nested. For the infra provider, well, there's tons of infra providers. There is the big 3 of hyperscalers. There's CloudStack, OpenStack, DigitalOcean. Well, I did not put all of them here. Well, it would be too much, but you got the idea. So what are the limitations for the vanilla cluster API for us? Well, the only thing we can use is kubeadm Bootstrap. Control plane also would be kubeadm, and there's no infrastructure provider for the Jquery cloud. And there is no control plane isolation from the user. There is no Jquery provider. Actually, I already mentioned that. And you need a Kubernetes cluster to create another Kubernetes cluster. And if you use kubeadm, you'll create 3 virtual machines for the control plane. And, well, it's kind of too much for the control plane, if you ask me. So this is how it looks like in vanilla. Pretty same, but less load balancers. And, well, we have a client private network. On every node, well, we have at least 3 control plane nodes and as much as you want worker nodes. In every node in systemd, we have a kubelet run by any container runtime. We use Creo, but it might be Docker or containerd. And kubelets start all the other pods. And, well, on the control plane side, it's basically vanilla kube, etcd, kube API, controller manager, kube scheduler, and Calico, or whatever CNI you use. And all the workload from the worker nodes access kube API through the load balancer in this private network. So is it perfect? Well, obviously no. We just discussed why it's not suitable for the managed Kubernetes solution. And is it good? Well, kind of. At least it's better than Magnum. So our implementation. We decided to not use free virtual machines for the control plane. They are usually underloaded and they spin, well, much more. The spin up of the virtual machine takes too much time than for the pod. So we decided to have some management Kubernetes cluster and have a namespace inside it. And it's inside those namespace, we'll spin up all the pods for the control plane for the users Kubernetes cluster. And all the custom resources for the cluster API would be stored in the same namespace. And, well, we'll have no virtual machines for control plane, which is cool. To do that, we had to write our own G-Core Bootstrap controller manager, and we had to create the new control plane controller manager. And our colleagues from WG, thank you guys so much, helped us with the infrastructure provider. And now it looks like this. Now we have two different private networks. One is on the client side, and one is for our management cluster. And on our side, we have a Kubernetes cluster with a namespace with all the control plane pods inside it. And there's a load balancer, which is pointed to the Kube API, and it has a public IP address. And all the workload from the client worker nodes access the Kube API through the internet through the public IP address. And we have access control list to restrict the IP address, so not all the internet can access it. Is it perfect? No. But is it good? Well, I guess it is. But what if the client would like to read logs from his pods? What if the client wants to do the port forwarding? What if the client deploys something with admission webhooks? Well, on that picture, there is no backward network connectivity. So Kube API has no way to access pods inside the worker node. But, well, we decided to use OpenVPN. How did it look like? We spin up the pod with OpenVPN server on the client side, on one of the worker nodes. And we create another load balancer, which is also publicly available on the IPv4 or IPv6. And inside the control plane, inside the Kube API pod, we just spin up the sidecar with OpenVPN client, which connects directly to this load balancer and to this server. And it brings the routes to the worker nodes, to the pods, to the services, right to the Kube API under its feet. And is it perfect now? No. Is it good? Well, it's better. So, but what if the client deletes something on the client side? What if he deletes the OpenVPN server? What if the client deletes the daemon set of Calico or Cilium and will lose the network? What if he deletes the kubeproxy if he's using Calico? Well, we have to reconcile it somehow because it's a managed service. So we use Argo CD for that. And it looks like this. So we set up Argo CD in the management cluster. And it has access to the API of the client's cluster right inside the same Kubernetes cluster. And it has the application for all the client's infrastructure, for kubeproxy, kubedns, for CNI, for OpenVPN server. So if clients use kubectl to delete something from the API, then Argo CD will reconcile it. And is it perfect? No. Is it good? Much better. And now the spin-up time moved from 20 minutes to 12 minutes. But do we really need two load balancers? Because, you know, Octavia and OpenStack is not that reliable, and it also is not very fast. And we can use connectivity instead of OpenVPN. And we can get rid of load balancer for each Kube API and use just a single ingress controller for the whole region, for the whole clusters, and then the client's API, Kube API would be exposed as an ingress, and we will use just a reverse proxy for it. And that's what we did. And now we have a single load balancer in front of the ingress controller, and all the kube API are exposed as the standard ingress object. And on every worker node, we have a special pod which is called KNC agent. It's the agent part of connectivity. And near every control plane, in every namespace, we have an extra pod for connectivity server. And it's basically an RPC proxy. So connectivity agent connects to the connectivity server. And then Kube API just uses as a proxy to access all the worker nodes on the client side. So we got rid of tons of load balancers. And is it perfect now? Nope. Is it good? Well, it's good, I guess. And the spin-up time is now just 4 minutes instead of 12 or instead of 20 at the start. So what if we want to add IPv6 support? What if we want to allow users to do more customization for Kubernetes components? What if we want to add more feature support for Cilium? Or we want to get rid of all of load balancers and add just BGP and so on and so forth. And actually we added IPv6 support. So I guess you got the idea. It's never perfect, but it's good for now. So what we got when we moved from Magnum to cluster API? Well, first of all, Magnum was pretty fragile. And now we have a stable reconcile loop. And if something goes wrong with the cluster, if it loses a node or two, if something happens, then the reconcile loop on every level will help us. If it's a loss of the node, well, then a new node would be created, just the same as the previous one. If it's something that client deleted inside the client's cluster and he should not delete it, then Argo CD would reconcile it. And, well, it reconciled it instead of ops engineers. We had long recovery because, well, the worker nodes were mutable and we had to log into it, and that picture with those cats. And now we have immutable worker nodes. We have golden image for every node, and every node can be recreated if anything goes wrong with it. Or even if you don't like it, you just delete it and we create you the new node, the same as the previous. And it saves a lot of time because finally all our clusters are the same. They are like cattle for us. We had no observability, so it was really hard to say anything about the Kubernetes API for our clients if we don't log in with SSH to that client, or if we don't use some dark OpenStack magic. Now, everything is a Kubernetes object. We can use the single kubectl for the whole region to look into namespace of some client's cluster and to check its kube API, to check how many resources he has, what machines he is using, what version of Kubernetes is signed for every machine, and even the OpenStack ID of the machine to make it easier to debug anything. So now we have two orchestrators in production. We have Magnum clusters in production, and we have cluster API clusters in production. And the funniest part is how to migrate easily from the old orchestrator to another. And the answer is there's no such way to do it in some, I don't know, not enormous amount of time and resources. So the only thing we could is to tell our clients, hey, we have a new orchestrator. It supports new Kubernetes version. You can use bare metal nodes inside it. We have Cilium in it. It upgrades really fast. It spin-ups really fast. We encourage you, please go to the new orchestrator. And if this doesn't help, well, you have to find your core clients. You have to find the clusters, and if they don't want to move to a new orchestrator, well, you have to do it for them. You have to provide the managed DevOps for free. And, well, that's the only way. So, to summarize everything, today we learned that, well, if you are thinking about evolution or revolution, evolution seems like, well, something logical, but sometimes revolution is the way more effective than evolution. Sometimes it's the only option. Pets versus cattle, well, we do love pets, but cattle win again. Well, automation really works. And immutable versus mutable. Yet again, cattle wins, immutable wins. Mutable is not working. Configuration drift is horrible. And live production migrations, well, are really smooth and easy. And nothing is perfect. There's always a way to do things better. And that's it. Thank you for listening to me, and any questions?
Thank you. Thank you. Please use the QR code, as always, to vote for the talk. And as expected, Andrei, you're welcome.
Thank you. I just wanted to ask, how do you manage OpenStack installation? You said that...
I'm sorry?
How do you manage OpenStack? You run those clusters in OpenStack, right?
Which one?
The tenant clusters.
The cluster API clusters?
Yep.
We have an abstraction. So my team is not responsible for the OpenStack, and we are not using OpenStack directly. We have Gcore Cloud API. So we are interacting with our cloud API, and it interacts with the OpenStack. And there's a separate team of engineers which are responsible for the OpenStack.
So you just moved this responsibility to their...
We didn't move it. It was originally their responsibility. And we are just happy client users, as you could be if you register on our website.
Got it. Thank you.
Let's talk a little bit about your clients so we understand the purpose of your platform as a service, because different companies, they create platforms as a service for different purposes. Some of them have internal clients, some of them have external clients. So can you please elaborate a little bit about Gcore business? Who are your clients and how do they use these Kubernetes clusters that you help to orchestrate?
Thank you for your question. Well, first of all, we are public cloud providers, so anyone could be our client. But we are more focused, historically at least, on the gaming industry. So it's really nice to have bare metal worker nodes in Kubernetes on the public IPs. Then you reduce the latency, and well, I guess that's one of our core features.
Mm-hmm. You mentioned OpenStack, yes, which is like own implementation of everything. As far as I remember, please correct me if I'm wrong, because I'm a system developer, mostly C++, Python, business automatization, all these things. I'm not DevOps. So I can be wrong is details. OpenStack and not OpenShift is more like a platform that competes with Kubernetes while using Docker images, while OpenShift, nearly the same name, is more like a Kubernetes distribution. Am I correct?
Yep.
So you are using OpenStack and you implement all these Kubernetes API within it. So basically you're like re-implementing Kubernetes within OpenStack. Am I correct?
Well, kind of. We are using OpenStack just as an infrastructure provider. So all we need from it is just bare metal nodes, virtual machines, and load balancers, and networks. So that's it.
Mm-hmm. And this usage of Kubernetes API as means of orchestration, you provided with analogy with zebra and ultramarine, which, by the way, is great. And this control plane API, like an ultramarine, but correct me if I'm wrong, control plane API is
cluster. Cluster API.
Yes. A cluster API is something closely related to Kubernetes. Yep. Yep. Why OpenStack is not that related to Kubernetes. So my question is, was there any other possible ways to implement with orchestration, not with cluster API, but maybe with different technologies like not ultramarine, but space marine, or maybe Slanesh daemons or something else? Or was the cluster API the only obvious choice? Can you please elaborate a little bit on that?
Well, I tried to skip it. So there was a slide with all the technologies that we could discuss.
And you skipped just to cluster API,
it will just
we will
take-
choose Slanesh, just because.
It will take just too much time, and it could
We
be
have
another
a little bit time right now, so please.
Okay, there is a bunch of technologies which allow to operate with different approaches to the spinning up the Kubernetes cluster, but well, I don't know. There's OKD, which is a free version of the OpenShift, and you can use this. There's Gardener from SAP. Well, it's pretty cool, but all of it is somehow related to the owner, and you have to get used to SAP or to the Red Hat. And the cluster API allows you to operate with clusters just the same way as you do it with pods. So, for example, you have a deployment, and it creates replica set, and it creates a pod. The same way you have a virtual machine deployment in cluster API, which creates a kind of replica set, and it creates a virtual machine, and you have rolling updates, and everything is custom resource inside the Kubernetes, and no other solution in the market. Well, might be other solution, but it's inside the Kubernetes community, and it's vanilla, and it just looks too good.
So it's popular within Kubernetes community, and it's reasonable to use it within your platform, despite that your platform is not Kubernetes per se, but OpenStack.
I think I didn't got the last one, but well, yep, it evolves pretty fast, and it's largely supported by the community, and yep.
Please.
Hi. As I understand, you use OpenStack as an infrastructure provider, and my questions: how difficult to manage OpenStack API with your API? For example, when OpenStack updates or their API something changed, how you support your API to follow this change?
Okay, thanks for the question. Well, it doesn't happen like, now your computer reboots and you have the new version of the OpenStack. Nothing like that. We kind of plan the updates, and it's well controlled. And our Gcore Cloud API is always ready for the version of OpenStack which is under it. And well, just both teams, the developer teams from the Cloud API and the operations team, which is responsible for the OpenStack, they collaborate and make the updates smooth and controlled.
Do you use some identity provider instead of Keystone?
Yep, of course we do. So actually, Gcore is more than just a cloud provider. We are also a CDN provider, streaming provider, anti-DDoS provider, AI services provider. And for all of that, we have a single Gcore account, Gcore user. So yeah, we have our own billing system, our own IAM provider, and all the, let's call it, core services of the cloud provider. So we are using Keystone for some cases, but they are mostly internal.
Thank you.
Thank you, Andrei. As for persistent volumes and load balancers, am I correct? Would you use persistent volumes based on OpenStack provided by Cinder, right? Or not?
Yep, we do.
And load balancers for applications provided by Octavia.
Yep.
And do you use the native Synthesis CSI plugin and Octavia?
No,
or
it's
your custom?
forked. So like I said, all the we are using G-core volumes under the hood. Yep, it's Ceph.
So it's
well,
not,
it's Cinder, yep. And the same, we are using cloud load balancers, and under the hood it's Octavia. So yep, it's forked. So it's not Cinder CSI provider. It's like G-core.
G-core provider.
Storage, yeah.
And what do you use for read-write many supported volumes?
NFS, we have NFS as a service. You can create an NFS server inside the project in the cloud. And then if you have a Kubernetes cluster in the same project, then you'll have a special storage class, and you can just use it to access the NFS shares from that share. And it's automated, so you have to do nothing to integrate NFS with our Kubernetes. It's out of the box. Well, I mean, the integration is out of the box.
Okay, thank you.
Implementing cluster API within OpenStack, how hard it is in lines of code? So atop of all the products and other existing software that you mentioned, how many lines of code did your software engineers wrote? Like thousands, tens of thousands, hundreds of thousands, millions, approximately, just ballpoint figures. How hard is it to create such a system?
Actually, I have no idea because I'm not a developer. I'm the ops guy. So I can only imagine, but I guess we can count. But I don't know. We can, but later.
Okay,
Well,
maybe you can spell it in man-months or in any other metrics. So how challenging is this task if anyone is thinking about repeating that?
I got it. So actually, we created the new orchestrator from the idea in the Confluence to the production. It took us like three guys from the dev team and 2 guys from the ops team and 1 project manager. So
And how many months?
I would say 9 months.
So it's pretty reasonable. It's not a small project.
Well,
but
9 months. 9 months to the general availability, but the beta started like in half of a year.
Yep.
Thank you. I have another question. Can you tell a little bit more about control plane implementation? How do you run it? Do you have your own operator, or do you use Kamaji? How do you deploy control plane actually?
So cluster API is for binaries, and we had to rewrite 3 of them. So yep, we have our own operator for the control plane, for the worker nodes, and yep, infra provider. So basically we have created our own control plane operator, which creates a namespace, which creates the pods inside it, which configures etcd to join the one to another, and starts Kube API and publishes. Well, there's a lot of more logic, but yep, it's what we did from the scratch.
So you have this service Kubernetes cluster that runs inside OpenStack, and it provides control plane.
Yep, inside itself.
And all those pods who runs etcd, this is also another operator, or is it part of your operator for running control plane, right?
Thank you for the question. That's a good question. Next question, please. So we are trying to improve it, and it's the next thing in our backlog. So yes, it's kind of operated by the code, but sometimes you need an ops engineer to fix it. So there's much more space to improve. But like I said, nothing is perfect.
How are you about going to open source?
We thought about it, but you know, you always have to to have some free time for it, and you have to tell the business why we need to go open source. But yeah, we have an intention, but I'm not sure when can we do it actually. Because you need to just make your code more pretty, take away all the dirty stuff related to, I don't know, some internal things. And when we do it, yeah, we probably would
And
go
some
open source.
good reason for business to invest into all these shenanigans to prepare the code for open source release, which is hard.
Yeah, just thinking that right now there are certain projects who start doing the same control plane provisioning, and they're developed much faster than your solution. I think that there might be a problem that in a while you will face with the situation that they will be more mature than your project.
Then we'll switch to the next.
Yeah,
and
but
we'll
it
contribute there.
might be
but
better that if we company group of people will work together on solving the same problems. So I think it might be better to just tell the community, hey, we have this solution, let's work together on solving control plane provisioning or etcd provisioning. Thank you.
I agree with you, but there's the business thing in it.
That's a good topic to discuss in our discussion area. I can see they are preparing after party.